Force is rate of change of momentum. SI unit will be kilogram meter second minus 1. This is for momentum, as momentum is mv, and rate of means division by time, which is by second. So it is kilogram meter second to minus 2. So for left hand side, it is meter second minus 1. For right hand side, it is force in Newton. In SI units, it is kilogram meter second minus 2. K is in over kilogram for mass, and for area, meter to power 2. Can make elimination to have right hand side meter second minus 3. So as both sides are not the same, we cannot say that it is homogeneous. Total momentum before equal total momentum after, certainly if no external force applied. We will apply conservation of momentum in horizontal direction, and before collision only the sac was moving horizontally with this speed. Its mass is 23 kilogram. After collision we have both boat and sac move as one object. So after collision we have 160 plus 23, okay, and it is the velocity after that is required. So we can make this product equal to 23 times 3.4, from which we can get V as okay. E2 is half M, which is 160 plus 23, that is 183, okay, times V squared. This is the velocity that we have just calculated. It was 0.43 all squared. This is half mv squared over E1, also half, and the only mass that has velocity before was mass of sac, which is 23, and it was 3.4 meters per second all squared. We can certainly remove half with half and use calculator to find the answer as 0.13. Certainly an elastic, and this is because E2 is less than E1, and this is shown here from ratio of E2 by E1 less than 1 means E2 less than E1. Okay, for the boat to be at rest, we should have weight equal to the up thrust applied by water on the boat. So up thrust is equal to, certainly it's not only the boat, it is the boat with the sack. Okay, so U is 183 times acceleration due to gravity. It will give some numbers that can be rounded to 1800 Newton. We know also U equal rho, density of liquid, GV, volume of liquid displaced. So it equals, by rearrangement, this was just calculated. I here converted by multiplying by 10 to minus 6. Okay. (1,000 kilogram meter cube minus 1 meter minus 3. This is a typical value for density of water. So we have here work against resistive force, and we know that work equal Fd, distance along the track on which there is resistive force. So F equals 5100 divided by D, and D is 23. Okay, it is clear that we will use the formula for delta GBE. So we should note here that changing kinetic energy from X to Y is converted to increase in GBE, okay, and in work done against the resistive force, work done to overcome this resistive force. Okay, so as KE at point X should equal work done against resistive force plus increase in GBE plus the remaining kinetic energy at Y. If we want delta H, we want delta GBE to be subject, so kinetic energy at X minus work against friction minus kinetic energy at Y, all divided by mg. This gives delta H directly. We can then substitute and make all the kilojoules as it is. Just multiply here by 10 to 3. Here is the mass will equal, okay, it will be less because although there is an increase in kinetic energy comes from the returning back to same level, so increase in delta GBE will go back to KE, to kinetic energy too, but from Y to Z we still have friction, so we will not have the very similar value of 13.1 as I remember, oh sorry, 16.1. We will not come here to Z with same value of kilojoule for kinetic energy, but it will be a little less than this value. So Ka at Z is less than this at X, which means V at Z less than V at X, and this is because there is friction from Y to Z. Okay. A moment is force times perpendicular distance from a point or a pivot. Moment of weight about B is 0 because line of action of weight is passing by B, or perpendicular distance is equal to 0. To calculate theta, it is obvious that we have component of t, vertical component of t here, which is t sine theta, and have same with the other side, and both vertical components should balance with weight because we are in equilibrium. So if we add these two up forces and equating them with the weight, okay, we can find theta. Okay, and say here 2 times think tension is given here, yes, 13 Newton. Okay, and if let the arrangement be in another step, here the weight is 19, so we can say directly that theta is sine minus 1, 19 over 2 times 13, which is 26. So theta is 47 degrees. Okay, we know that Young's modulus is the stress over strain, and we have the strain, we want the strain, and we have both stress and area. We have the diameter, so we have area. So from this equation, we can rearrange like that, sigma over E, and sigma is, sorry, we have here youngest modulus, but sigma, we don't have sigma. So we need to dismantling it to force over area times 1 over E. The force on the wire is the tension, okay? And value of tension is 13 Newton. So it is 13 over area, if this is the diameter. Radius will be 0.4 millimeter, which is 0.0004, okay, meter squared times pi, this is the area, times 1 over value given for Young's modulus, 9.3 times 10 to 10. Okay. Your calculator, you should find the final answer as okay. We have equation of motion S equal ut plus half at squared, u is 0, ut is neglected, and t by rearrangement is square root of 2s over a. So okay, so from another equation of motion, v squared we can find easily by again neglecting u squared, because u is equal to 0 from rest. We have square root of 2a square root of s. Square root of 2as is same as square root of 2a times square root of s. So the relation here between s and v is not linear. It is a root function, and root function is drawn like this. Okay. We can also calculate the exact value of speed at the 1.6 meter. If you plugged this 1.6 in this equation, you can get the value of 5.6. Period time of one complete oscillation. Amplitude maximum displacement from equilibrium. Okay. You can say this is antinode, this is antinode, this is antinode. V is equal to lambda f. We have here f of 25. Just need lambda. We have from the figure here length of string and how many nodes and antinodes form on this length. I see here a 1.5 lambda to be equal this length, which means lambda equals 0.64 meter. We can substitute here, so V equal 25, which equals, okay, when frequency becomes 30, this means lambda equals V over F, 16 over 30. I choose 16 because it doesn't change the speed. So lambda after the increase in frequency will be this value. And if we divide the length over half of this value, this is the wavelength, half of wavelength. Okay, if we divide total length over half of wavelength, we will get 3.6, which is not a multiple of lambda over 2. And to have a stationary waveform, we should have length of string to contain multiples of lambda over 2. Okay, and lambda equal the sine theta, and we need n, so it is d sine theta divided by lambda. D is 1 over line's density, which is given in question as, okay, sine theta is sine 37, and 1 over lambda will be 1 over 4.5 times 10 to minus 7. This all gives this value. Okay, we will round this value to 1. We will round it down, so n is equal to 1. Okay. Having fewer lines density means n decreases, 1 over n increases, 1 over n is the d. Okay, and we have sine theta from the equation L lambda equal d sine theta. We have sine theta to equal n lambda over d. Okay, as d increases, sine theta and theta will decrease. As sine theta decreases, we know that sine theta is also equal to x over d. X is the distance from the bright spot, and d is distance from the grating to the screen. So as sine theta or theta decreases, x should be less, and as x decreases, spacing between fringes also decreases. Okay, rate of charge flow. Okay, to draw this relation between terminal potential difference and current, we need to remember that this relation is VB minus IR. Okay, so this is a straight line equation with some part cut from the y-axis, and this part is VB. VB here is 1.5, so we will use the rule starting by 1.5, and we should end somewhere here. If we looked carefully, we will find that internal resistance, which is 0.57, is the slope. Okay, we can certainly write IR as RI. Here is X, here is Y, so this is the slope, and we can make this slope here clearly. If this was to 1.8, 2, if it was like that, we would have to just make this line to the 2, because we have 1.5 as a vertical difference divided by 2 as a horizontal difference. This certainly gives you the slope of 0.75, but the graph just ended at 1.6, so we cannot draw this line to, for example, cannot draw it like this. We should draw it up, but where is exactly up? It is simple to find if we substituted 1.6 in this equation. So we have V, which is equal to 1.5 minus 0.75 I. Okay, if we substitute I by 1.6, we will have the value of 0.3 volt. So we should stop somewhere here at 0.3 volt. If all of this is 0.5, so very small square is 0.05, and to reach 3, we reach 0.3, we can simply divide like this. We will get 6 very small squares. So this line should be adjusted just to have 6 small squares. Okay. Okay. So resistivity from R equal rho L over A. Rho is equal to RA over L. Okay, R is given, A is given 2, and L is given 2. So we have here the answer. Oh, okay, meter. And if we want to calculate R, okay, we can do this, calculate the total resistance in the circuit. It will be this R times the resistance of the wire, okay, divided by and in the same time R total is equal to the terminal potential out of the battery, which is VB minus current in circuit times internal resistance, which is potential drop across the internal resistance. So VB minus this potential drop gives the potential between the terminals. This potential is applied on R. So if we divide it by the current, we can find R. Okay. Okay. Oh, sorry, we can only find our total, not I through R, because if we want to find R from terminal potential, we should divide by I in this branch, not I in the circuit. I in circuit is divided to two parts, I1 and I2. So if we were to just divide terminal potential by some current value to get R, this current value should be I1, but we don't have I1. So if we divide terminal potential by total current in circuit, we get total resistance. Okay, just be careful when applying Ohm's law. Know specifically which current with which resistance you apply the law or the formula to. Okay, this gives us our total as, and we can substitute in this equation and rearrange. We can find something like that. Okay. Just I made a cross product here. Okay. From this, you can easily get R as this value. Power dissipated, it is I squared R. Okay. And once again, be careful for which resistor the question asks about. So it is the internal resistance R small. So current in circuit, this is the current that passes in the internal resistor. And this is the value of internal resistance. And the answer should be certainly in what. Okay, structure of nuclear atom. It is a nucleus, okay, where mass and positive charge are concentrated, okay, and electrons outside that revolve in orbits, okay. Two elements, one with 94 and one with 91 protons, okay, both decay form 92 protons with respect to B. This is a decrease by 2, so it is alpha. With respect to Q, this is an increase by 1, so it is beta negative, where neutron is neutron decay to proton and beta negative, and electron anti-neutrino. So we know that charge is 1.6. This is the elementary charge. And if we divided it by mass of proton, we will not get this number. If we divided it by mass of proton, mass of electron, okay, we will get this number. But here is a positive sign, so this is positive, so particle is positive, beta positive particle. Thank you for watching. Keep following us.